Welcome to CS 101, Scientific Python, Lecture 21, our third lecture on optimization, in which we will talk about Monte Carlo methods. Monte Carlo methods refer to introducing the use of randomization in solving problems. Today we're going to start off by talking about two methods, random sampling, and then in particular a random walk algorithm. We're going to use that on a one-dimensional problem. Then we're going to apply a library basin hopping algorithm to optimize a 2D problem. And then finally, we'll summarize the strategies of optimization that we've seen so far and talk about the different kinds of problems that these apply to best. Random sampling describes a scenario in which you have a function and you want to choose a set of points at random, sometimes within a constrained space. Basically, you're just picking a bunch of random points and you're hoping that something is near the actual maximum. Random sampling works best if you do know where to focus your search. It's most helpful if you're trying to simulate actual data samples, but it's worth mentioning as an option anyway. It doesn't converge on a global solution because it doesn't converge at all. It's not an iterative method. But it can help you identify where to search more thoroughly, for instance, if you're going to use a greedy algorithm or something else afterwards. Our analogy is that we're simply going to pick a bunch of random points in the region of a hill and accept the tallest of these as the highest point. Of course, the pitfall is, without good constraints, we're likely to miss the optimum value. Let's look at this for a particular problem. First, we're going to set up a figure of merit f. F is just going to be our function. We're going to select a set of candidate guesses randomly, which are x, and we're just going to keep track of the best solution. We're going to look at the statement f of x equals sine x minus 0.02 x squared. After importing numpy and defining f of x, we go ahead and set up a set of points x and y across the entire range. This will let us plot the actual function so that we know what the actual function looks like for comparison purposes. In practice with random sampling, you wouldn't do that because that's effectively a brute force search and you would already know. We're going to select 50 points. We're going to use randint to select indices inside of our range inside of our array x. We're going to build a y samples up from pulling each of those points. We're going to keep track of the highest one, and then we're going to plot these results. So the red line will represent our actual function, the blue dots will represent all of our samples, and the blue X will represent the actual maximum. So in this case, you can see we've identified a lot of points left and right. If we look near the top, we'll find that we've identified a point that's reasonably close to the true maximum, but doesn't quite hit it. So this gives us an idea of where to start searching if we're looking for a maximum, but it's not good for identifying the maximum in and of itself. Now imagine for a moment swirls of autumn leaves. These leaves settle into low-energy leaves in the wind, for instance, next to a building or bench. The leaves still scatter out and travel around, but they prefer to rest in lower energy states. A random walk is something like the leaf, searching through the function space for the minimum value. So what we're going to do with a random walk is we're going to take a current candidate solution and we're going to tweak it randomly. Think about that leaf blowing around. And if the solution is better, we always accept it. A leaf tends to settle. But if the solution is worse, we sometimes accept it. Sometimes leaves blow away from the pile. You can also think of this as taking random steps as a person near a hill, but maybe not accepting the step if it's worse. The pitfall is that random walk methods converge slowly, and they can still miss the best candidate solution. But it does have a way from getting stuck in local maxima or minima. The process for a random walk algorithm looks like this. We're going to set up a figure of merit f. We're going to select a starting guess x naught. we're going to change a random feature of the guess. In other words, we're going to push it in a random direction. If this improves the solution, then keep it and cycle back to step 3. If it does not improve the solution, we still keep it sometimes, and then we cycle back to step 3. Since we need to have a way of deciding when to end a random walk, we're simply going to set a predetermined number of trial changes to do. Let's examine this with our function from before, f of x equals sine x minus 0.02 x squared. This random walk code begins by defining f of x, as we would expect. It sets up a grid of x and y points so we'll be able to plot the entire function as we saw before. Right now that plotting code is commented out for ease. But let's take a look at this random walk algorithm closely together. We choose a starting guess. We could choose this randomly. We're just going to use -20. And then we set up a step size left and a step size right. This looks like the greedy algorithm that we saw previously, in which we had to make a decision which way improved our solution. We're going to start counting from 0. We're going to go up to 10,000 steps. Our current best x that we've seen is -20. It's our starting guess. And the current best f is f of -20. We're going to set up steps so we can track the history of the points that we have. Strictly speaking, this isn't necessary, but it makes it a little bit easy for us to plot some of the consequences of this. Then we're going to have our main for loop. We're going to take a random step with a 50% chance in each direction. The random numbers of chance are uniform random numbers. So we're going to take a uniform random number. We're going to see if it's less than 0.5, we step left. If it's more than 0.5, we step right. We compare our trial x against our current x. If the solution does improve on our current solution, we always accept it. So we set x equal to trial x. If the solution does not improve our current solution, sometimes we will accept it. In fact, under the current circumstances, we have to accept it most of the time to really explore all of our options. So we're going to set that at a 90% chance of accepting a bad answer. We are going to track our best solution, and we're going to print that information out at each time step, and we're going to log our steps for plotting later. Then there's some plotting code at the bottom that's going to plot the line, the function itself, as a red line, and it's going to plot the points that are visited by this random walk as blue dots. So here we can see that it has explored everything pretty well. We zoom in, we can see that it started here at -20, it walked uphill, it walked around, and although you can't see it for sure here, it would have been walking back and forth as it carried out these operations. We can plot that as well by using steps. And here, this is sort of a sideways view, where we're viewing the value of I across the x-axis and the value of x that was currently under consideration as a candidate solution. So you can see these tiers where it walks up to a local maximum, and then sometimes it makes it out of that local maximum, sometimes it goes back down, wanders up and down, but it tends to stay close to the tops of these local maxima. There are some videos you can explore which illustrate the value of the likelihood of accepting a bad answer. This video is one that we would consider too cool, or in other words, it's not likely enough to accept a bad answer. It wanders around some, but it has a hard time actually getting out of this local minimum, even though it does wander up to the left repeatedly. There's another video that's too hot. It starts at a certain point, and then it's too likely to accept bad answers, so it's basically just wandering wherever it wants to go. It does spend some time wandering around local minima, but it wanders so much over time that it never really makes it down to the center. Finally, there's a video that's just right. This one wanders back and forth to the left and right pretty equitably. It successfully locates the true global minimum for this function. and it doesn't spend too much time wandering away. Or maybe it does. That's one thing that happens with random walks. They're unpredictable. We can also take a look at a two-dimensional example. I give you the full code for this example as well. This one requires the ability to step left and right and forward and backward with equal likelihood, so that you're going to see 25% chances of stepping in each direction. We're going to constrain the area that we're searching to +1 to +5 on both x and y dimensions to limit the amount of values that we're going to have to look at here. This is a long code that in most respects is quite similar to the 1D code that we saw a moment ago. It's going to have slightly different probabilities for looking at everything. It's going to wander around a little bit differently, but you'll be able to see how it traverses a lot of points inside of this function randomly in its search for the true global maximum. So here you can see how it's wandered around some of the lower hills, but it never quite made it up to that global maximum sitting there around 1.5, 1.5. So this is a flaw that many times you find in random walk algorithms. However, they're really good when you hybridize them. If you have a greedy algorithm that gets stuck, one good approach is to randomly restart it with several new configurations. Then take the maximum value of all of these. In other words, we've hybridized random walk or random sampling, either one, with hill climbing. We'll take a look at what that looks like in the basin hopping algorithm in a moment.